Buongiorno! I'm sorry I've been a bit out of the radar for the last few months because I've been traveling and focusing on my PhD, but I ended up actually in Italy, and today I am inside a reverberation chamber at the University di Politecnica Marche in sunny Ancona, Italy. So today I'm going to show you how to use this fascinating facility to perform a shielding effectiveness measurement that is typically performed inside the anechoic chamber, but it can also be performed in a reverberation chamber in accordance with IEC 61000-4-21 standard, and we're going to do exactly that. And according to the definition of this standard, a reverberation chamber is a room specifically designed to have a very long reverberation time. But what does it mean in terms of electromagnetic fields and waves? That means that inside the reverberation chamber, the propagation distance is artificially increased through reflections to extremely long distances, which basically fade according to Rayleigh distribution. And in other words, we have a Rayleigh distributed field inside a reverberation chamber. So that is achieved obviously through reflectors. So we have, if you look inside the reverb chamber, it just have many reflecting surfaces positioned at the four corners. In addition to that, we also have a stirrer that creates the randomness of the environment variation. So in order to put the theory into practice, we're going to show to you today how we test shielding effectiveness of reinforced concrete samples. There are several papers on this topic published by this research group, which I'm going to link in the description. But the main idea behind this experiment is to show how reinforced concrete samples improve isolation from electromagnetic fields in buildings. And basically this is achieved through the shielding effectiveness measurement, and which is compared against non-reinforced concrete samples. In this experiment, we will use a nested reverberation chamber approach, where we will have a small shielding enclosure inside the reverberation chamber, and inside we will feed two antennas and the sample. Sample will be placed at the boundary such that it penetrates, the electromagnetic energy penetrates through the sample, and then we will have another two antennas inside the big reverberation chamber, creating the Rayleigh distributed field in there. And by looking at the difference in S parameters between internal antennas and external antennas, we will obtain the shielding effectiveness of this sample. And then we can compare it one sample to another. We can also compare it against a flat metal plate as a reference of noise, and etc. So this is the main idea behind the experimental setup. As you can see, a reverberation chamber is quite different to an anechoic chamber that you have seen in my previous videos. Instead of using absorbent material on the walls, reverberation chambers have reflectors. So every wall of a reverberation chamber is effectively a mirror that is designed to reflect electric field waves back to its origin. So in a reverberation chamber, we have an infinite almost amount of reflections, and we cannot even distinguish line of sight anymore because we have a very complex multi-path environment. The history of reverberation chambers doesn't actually go very far back. It's only been developed throughout 1980s as an alternative to complex and expensive anechoic chamber setups. And since then, various measurement techniques have been proposed to replicate or basically have an alternative to anechoic chamber measurements. And since then, these standards such as IEC 61000-421 have been designed and put in place, and now this type of measurement is quite common for automotive industry, for example, as well as radio wireless communications, where we use reverberation chambers to evaluate throughput variability. So we simulate, for those of you who know these terms, a Rieschen channel, which is a multipath reach channel with many reflections, and we can simulate that using a reverberation chamber and introduce various degrees of uncertainty through its steerer. So this thing here, it rotates, and this steerer allows to create a chaotic environment inside the reverberation chamber, which is something that you would experience in the field use as well when you deploy your smartphone in various environments. So you want to be ready for any kind of scenario. And that's why you would use a reverberation chamber to create the worst case scenario for your device. Let's take a look at the enclosure that we're going to place our device under test into. So it looks like this massive metal box, but we're only going to use a small part of it. So inside the metal box, you will find we already have placed two horn antennas here. For the shielding effectiveness measurement in a reverberation chamber tool IEC 61000-4-21 standards, typically the measurements of S21, S31 and S34 are performed. So S21 is effectively the antennas outside the enclosure or the small reverberation chamber. So this is a nested approach, remember. And then there are two antennas inside, and these are S34, and so that's two measurements between antennas outside and one measurement between antennas inside, and then the measurement from S31 shows us the shielding effectiveness, so that there is the effect of the enclosure. In fact, all those S parameter measurements are performed with the steerer enabled, and the rule is that the steerer must complete at least one full cycle at each frequency point. So the frequency points are also divided for the so given a specific band, the frequency is divided in bins, and each frequency bin is measured separately. And for each frequency bin, the steerer must complete one full turn. And then the sample is also removed, and the measurement is performed without the sample. So the important part is to perform two measurements, one with the sample and one without the sample. The extraction process then is performed online to get you the exact shielding effectiveness ratio between the reference power and the power with the shield. So now we are all set up to run the measurement with the sample in place. And as you can see, this is a concrete sample. So we effectively, the objective of this exercise is to measure the shielding effectiveness of different pieces of concrete as you've seen. So now the sample is really stable. As you see, there are more than 17 different types of these concrete blocks. that we have here, and each is exhibiting slightly different properties. So the objective of this is to measure different samples of concrete. And there's an interesting observation. These concrete samples have 2 years stability time because they initially contain a bit of moisture inside the fresh concrete, and this moisture slowly evaporates, and after about 2 years it becomes stable, and then the concrete block actually shrinks in size slightly, and this block is stable now, and the measurements are quite repeatable in this case. However, previously with a fresh concrete block, the measurement of shielding variation, shielding effectiveness can vary quite a bit.
Okay.
Carbon oxide.
So there's all kinds of different samples with different materials inside, each numbered.
But we also have to be careful because there is some iron pieces that can burst you. But the zip is
Some other samples.
it's terrible for you cannot use the zip because the zip reduces too much.
It's probably not very uniform impedance.
Or we have to find a zip with a metallic part,
Okay.
but is not metallic, and there is just a longer patch.
It's just like a hole, yeah. Okay, so yeah, this can be used instead of that gasket. Okay. Placed using the same measurement method. So the external antennas are placed at almost random positions inside the reverberation chamber. It doesn't actually matter where they're placed, but we use dual polarized horn antennas as antenna 1 and antenna 2. And they just point at different parts of the reverberation chamber, but again, it doesn't exactly matter where they point, because if a reverberation chamber is calibrated properly, it makes no difference.
The higher wires are more stable because
So this is when we stopped the stereo. You see that the fluctuation is effectively a lot less, but we still see some fluctuation. And Franco, if you start it again. Okay.
Lower higher frequency, down speed rate, slower.
yeah, maybe lower because it better. It is 5 degrees per second.
Okay. So now the stereo is working again, and we see.
Also, the iron values are changing.
Okay.
Okay, you can try 1 degree per second. Stop.
One degree per second. Uh-huh.
And now,
Relatively high frequency, measuring from 6 to 7 gigahertz with 1 gigahertz span. And you see all the chaosity introduced by the stereo. Okay. So the different modes. So what is this 5? What was it?
degree for second of rotation.
Yeah,
5 degrees for
5 degree per second.
Yeah.
Okay. Degree of rotation of a stereo. Okay. And this is the stereo, so it rotates at a specific speed. At this moment, it rotates at the speed 5 degrees per second. So, as you see, this aperture is relatively large for high frequencies. introduces more effect, but at low frequencies they would be smaller, so the effect would be less, so it affects more the device at high frequencies and at a low frequency. Now you see the horn antennas pointed at the steerer, so that we introduce a lot of curiosity inside this reverberation chamber, and this is actually in fact a brick inside the tin foil. So this is what the steerer looks like when we operate it inside the reverberation chamber.
Actually, in this chamber we have a second steerer, and so those two steerers can work together to create even more control over electromagnetic fields inside the reverberation chamber. So most chambers don't have that. In fact, it's not required by the standard to have more than one steerer. But in this case, because it's for research, we have more steerers, and the additional steerers have more degrees of flexibility of achieving higher degrees of multipath environment. And in fact, it is making it more realistic, because in realistic environments you have more than one degree of variation. There's typically many people moving, cars, vehicles, etc. So all of that is acting a bit like a steerer on its own. Also, in terms of frequency, this particular chamber can generate waves with wavelengths as much as 6 meters. So that wavelength corresponds to about 25 megahertz as the lowest mode of this reverberation chamber, and at around 100 to 200 megahertz we have here up to 64 modes already operating, and that is a very well steered reverberation chamber environment when you have many modes. And it goes all the way up to 60 gigahertz, where this measurement can be performed here, but the attenuation of high frequency signals becomes really difficult to control, but it can be done and all the way up to this frequency, and it is being used for testing of commercial millimeter wave antennas that are operating at around 28 or 26 gigahertz. So FR2 millimeter wave range.
So this is now we're showing S31, so the antenna inside the nested chamber or small reverberation chamber. So we see it's now the steel variant, and we're going to turn on the steerer back. There's more of that. But we don't see actually as much the spurs as we've seen with very narrow span.
This is 1 gigahertz of span.
Yeah.
If you want closer.
Okay.
For example, if we can, yeah, we see how to do.
Oh, there you go. Yeah, single.
Single. You can better, if you press, you can better appreciate the variation between one position.
Yeah. So we can see how much actually. Yeah. Okay, that's quite a lot of variation between different measurements. So that's just with introducing the steerer at 5 degrees per second. Okay.
And if we go to a single frequency, and we make continuous, but okay, and
Yeah.
we can lower the sweep time.
It will be.
We
Okay.
can increase the sweep time. For example, you can see at a single frequency the variation of the S31 parameter.
Okay. So okay.
Here we have 20 seconds.
With a 20 second sweep time, with a variation of S31 at a single frequency. Okay. And what does the standard tell you to do actually? Does it have any specific parameters?
For the student thinners,
Yeah.
we have, of course, first to calibrate the DNA. Then we have to measure the S21, S31, and S34, I think. And then we can calculate the shielding thickness.
Okay. And do you use a stereo on this measurement or not really?
Yeah, use stereo.
You use stereo.
Yeah, because we have to average over all the position of the stereo.
Okay, so an average of all positions of the stereo.
For each
So
person.
the stereo needs to complete one full cycle.
Yes, at least one.
At least one full cycle at each frequency, right?
Yeah.
Yeah. So we're ready to start the measurement, and we close the door of reverberation chamber. Now is running the measurement. Is the stereo is zero? Is it? Is it at zero?
Yes.
Yeah. So at its first position, and the measurement will be performed at 400 megahertz chunks. And now it's just moving inside to reach the zero position, and then it will begin the measurement. Okay. Now it's at the zero.
Okay.
You see now it's measuring, and it's capturing, like I said earlier, S21, S31, and S34. There are three types of data that is capturing of those parameters, and then the post-processing inside the computer, it performs the calculation of the shielding effectiveness automatically. And all with the consideration of all the standard equations shown in the IAC 61000-4-21. Now we're just seeing on the output, basically, we can go to the measurement and see S21, and that is selected. And if we go to format, we can see the linear, that the measurement is being performed in the linear mode, and when it's finished, it goes to the polar mode to output it. And this is repeated with 400 megahertz steps throughout the bandwidth, all the way up to 8.4 gigahertz. So at this single position of the stereo, there's quite a few frequency bins, which the size of the bin is 400 megahertz, and then there's inside how many points? 1,600?
Yes.
1,601 point inside each frequency bin.
So after this measurement is complete, we're going to remove this concrete sample and repeat the measurement without it. And like I said, then the third step will be to put a flat metal plate to cover the hole, and again repeat the measurement to establish the dynamic range. But you only need to really do this once in this case, and this type of measurement has already been done before. So we're just showing you an example of how this measurement is performed. So we already have the data, in other words, and we're just going to use this data, and I'm going to show you how the results look like. So now that we performed the experiment, we need to analyze the data and obtain the shielding effectiveness on its own. So to do that, we use post-processing tools, and in particular in MATLAB, which I'm going to skip for now, but the idea is basically to export S parameters and divide one S parameter by another, external to internal. Now I'm going to skip this part and just show you the results from the post-processing step, and this is effectively what we're seeing as the main figure, which is showing the flow level. The flow level in this case is when we fill the hole with a perfect reflector, so with just a flat metal plate. So that means there is no hole in the enclosure, and the enclosure is a complete Faraday cage. Now, this is the floor level, and then the blue line is the original non-reinforced concrete sample, meaning that it doesn't have any iron fillings. And the red line is the reinforced concrete sample. So the reinforced concrete sample means that it's got iron fillings which have been mixed with the concrete and randomly distributed. Then on this figure we also can see how the shielding effectiveness is changing over time. So we can see that after 28 days and compared to 35 days, there is a significant difference, as I was saying, due to basically moisture vaporizing from the concrete sample, and it becoming overall slightly lighter and of different composition. So there is a bit of a settle time associated with the sample, and we can see that after about 42 days and 49 days it becomes more consistent. However, still at 77 days there are differences between 49 and 77 days, so the shielding effectiveness does vary over time. Then finally, the last figure is showing the ACS, which indicates the actual effectiveness of shielding, so and how much energy is blocked compared to the non-reinforced concrete. And we can see that we achieve quite a significant improvement with a reinforced concrete sample. Let's also talk a little bit about how exactly those samples were made, the concrete samples with iron fillings inside. So we can have a look at this slide. So we see that the cement type was Portland CM 52.5R, and this is the inclusion of brass-coated steel fibers which were randomly distributed, and almost like a very fine quartz sand. So this is very small filling, and then the cement has been added to those fillings, and it was poured into these discs. So you see all the settings here, and finally, very important is that the sample of the reinforced concrete must make contact with the frame around it to ensure that the shielding is adequate and continuous, like our normal EMC concept, so that when we design an enclosure around an electronic product, we want to make sure that the shield is as close to Faraday cage as possible. And this is exactly the same concept shown here, so that the sample is poured exactly to the dimension of the frame, making sure that it makes a conductive contact with that frame. And then the frame is mounted into this enclosure which we used during testing. If you're interested on this slide, you can also see the graph and what we've done today. So you see we had two antennas outside and two antennas inside, and there was an inner chamber and an outer chamber. Then we obtain with a VNA S parameters of S21 as internal antenna 1 to internal antenna 2, then S31 internal to external, then S34 external to external, and S42, which is not important, but we recorded all of these, and then we obtain these shielding effectiveness figures by running those calculations as shown here. So we see that the main ones that taking impact are S21, S41 and then S43. So these are the parameters that are being used in calculation. So I hope you enjoyed this video and it was insightful for you. Today we looked into how we perform the measurement of shielding effectiveness in a reverberation chamber, and we used a concrete sample to illustrate that with a reinforced concrete and a non-reinforced concrete, such that we could compare them in terms of shielding effectiveness. Please like and subscribe this channel, and I'll see you soon in the next video.